Unit cells can be broadly classified into two categories: primitive unit cells and centered unit cells. Unit cells in which all the constituent particles, such as atoms, ions, or molecules, are present only at the corners, are called primitive unit cells. Unit cells in which one or more constituent particles are present at positions other than its corners, in addition to those at the corners, it is called a centered unit cell. Based on the position of the centered constituent particle, centered unit cells are categorized into three types: body-centered unit cell, face-centered unit cell, and end-centered unit cell. A body-centered unit cell has constituent particles at all its corners, as well as one particle at its body center, as shown here. A face-centered unit cell has constituent particles at all its corners, as well as at the center of each face. An end-centered unit cell has one constituent particle at the center of any two opposite faces besides the ones present at its corners. You know that a three-dimensional crystal lattice is generated by the translation of lattice parameters A, B, and C. Based on lattice parameters, we have 7 popular crystal systems, namely cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic, and triclinic. Let's discuss each in detail. In a cubic crystal system, all the 3 axes are of equal length and are at right angles to each other. The possible lattices are primitive, body-centered, and face-centered, as shown here. Sodium chloride, zinc blende, and copper are well-known examples of this type. In a tetragonal crystal system, the 3 axes are at right angles to each other, but only 2 are equal. The possible lattices are primitive and body-centered. Calcium sulfate and titanium dioxide are examples of this type of crystal structure. In an orthorhombic crystal system, the 3 axes are unequal, but all axes are at right angles to each other. The possible lattices are primitive, body-centered, face-centered, and end-centered. Rhombic sulfur, potassium nitrate, and barium sulfate are examples of this type. In a hexagonal crystal system, 2 edges are of equal length. 2 angles are of 90 degrees and 1 angle is of 120 degrees. The only possible lattice is primitive. For example, graphite, zinc oxide. In a rhombohedral or trigonal crystal system, the three axes are of equal length and inclined at the same angle, but the angle is not equal to 90 degrees. The only possible lattice is primitive. Calcium carbonate and mercuric sulfide are examples. In a monoclinic crystal system, the three axes are of unequal length and only two angles are of 90 degrees. The possible lattices are primitive and end-centered. For example, monoclinic sulfur and decahydrated sodium sulfate. In a triclinic crystal system, the three axes are of unequal length and all angles are different, and none is equal to 90 degrees. The only possible lattice is primitive. Potassium dichromate, boric acid, and copper sulfate pentahydrate are some examples. You already know that every crystal lattice is made of an infinite number of unit cells, and every lattice site is occupied by a constituent particle that may be an atom, an ion, or a molecule. Now let's examine what portion of each particle belongs to a particular unit cell. Consider three types of cubic unit cells. For the sake of simplicity, assume that the constituent particle is an atom. Let's start with a simple or primitive cubic lattice. A simple cubic lattice consists of 8 atoms at the 8 corners of a cube. In the open structure shown here, the distances between the atoms are greatly exaggerated. In reality, the atoms are packed much more closely together, as shown in the space-filling model here. The space-filling model shows that the atoms touch along the edges of the cell. By considering the portion of atoms inside the cell boundary, we can generate a unit cell of a simple cubic lattice. From this, it is evident that each atom at the corners contributes 1/8 of its original volume to each unit cell. There are 8 atoms at the 8 corners. Thus, the number of atoms in each unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. A body-centered unit cell contains 8 corner atoms, just like in a simple cubic unit cell. However, there is one more atom at its body center. As a result, the atoms at the corners no longer touch along the edges of the cell in the space-filling model. The unit cell of a body-centered cubic cell is shown here. It is clear that the 8 atoms at the corners contribute 1/8 of their actual volume each. In addition, one atom lies completely inside the cell. Therefore, the number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. There is one atom at the center of the cube. Thus, the total number of atoms in a body-centered cubic unit cell is 2. The face-centered cubic lattice consists of 8 corner atoms, just like in the simple and body-centered cubic lattice. However, it also contains 6 more atoms at the 6 faces of the cube cell. The atoms touch along the diagonals, and each touches 4 corner atoms. A unit cell of a face-centered cubic cell is shown here. It is clear that the atoms at the corners contribute 1/8 of their original volume each. In addition, there are 6 atoms at the 6 faces, which contribute half of their original volume each. The number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. The number of atoms present at the faces per unit cell is equal to 6 atoms at the faces into half an atom per unit cell, which is equal to 3. Thus, the total number of atoms per face-centered cubic unit cell is 4.